the domain. Thank you. So as for the algorithms, again, I will not present them in this paper, but arguably the algorithms, the algorithmic part is not that interesting. I mean, it leads to some results, but the most, to me, mathematically, the most interesting problem is encapsulated in just like asking about general min-max non-convex-nonconcave problems with a small diameter of the maximization set. The algorithms, they are, again, you will see why I'm referring to algorithms as being not that interesting, although they're useful practically. And again, you can see the paper for this kind of stuff if you're interested. So roughly, the paper is comprised of two parts. One part is the approximation theory, asking general questions about maximization, min-max problems for the small maximization domain, and answering these questions. And another part is algorithmic. It's how to solve these problems in a regime where the previous theory allows to solve them. And this second part I will not touch in this talk at all. Again, so here we go. So first of all, let me give some background. Smooth. First of all, I'm always talking about smooth min-max optimization problems. What it means is we have a function f of xy of two variables. Variables are constrained to the known convex subsets, convex bodies and the corresponding Euclidean spaces, x and y. In particular, x might just coincide with the whole space. In this case, the problem is unconstrained in x. In y, the problem though is constrained always. The set y has to be bounded in this framework, and this is not too much of an assumption. This is if you're familiar, for example, with non-convex-concave optimization, it's quite natural to assume the bound on the domain y. So you can think about it as a way to make the primal function that is to be minimized. So this max of y of f of xy is the max function. So first of all, we want it to be defined, right? And one way is to have a compactness of the domain, and we actually want the result to be attained in y. So in other words, we assume that y throughout, I will assume that y is bound, and it has d is going to be the bound on its diameter. Okay, so let's first recall the usual convex concave setup. No, sorry, first of all, the general min-max setup. So I assume that f is smooth, namely it has Lipschitz gradient. So both components of the gradient are Lipschitz. For now, let's assume this. We have a full knowledge of, usually we have a full knowledge of the sets x and y, and we can compute the corresponding proximal mappings. All right, so we can essentially we can have the projected gradient steps, gradient times the gradient steps. Function f is so our black box model in this setup corresponds to not knowing exactly the function f. So at any point x, y, we can query, let's say, first order oracle to the function f. Later on, I will talk about, like, I will in the algorithms, we actually will have to query algorithms of the higher order. I will not talk about it right now in much detail, but the point is that it's still, it's kind of quite natural from the theory that we consider, and anyway, the access to the function is local. The question is, what is the order of the oracle? So in the iterative methods, we form a sequence of points that would approach such that the corresponding function values approach the f star, which is the value of the min-max. Okay, so we know that at least in the convex concave setup, we know that this value is attained under very mild constraints. So for example, if y is bounded, it already suffices to for a saddle point to exist, well, at least it suffices for the f star to be defined for sure. And actually for the Minimax theorem to hold. We will see it in the next slide. And so complexity of solving such problems, let's say in the class of problems with Lipschitz gradients, so the class of first order smooth problems, is the number of iterations to guarantee a given accuracy of solving this problem. where the question is how to define accuracy. What is the criterion that is of interest to us? So to understand this, so let's recall first the usual convex-concave setup, right? So the classical setup. Convexity concavity means that the criterion is convex on X for any fixed Y, and vice versa in Y, concave in Y for any fixed X. Set. So we know that under weak assumptions, so for example, Sion Minimax theorem holds as soon as one of the sets is bounded, we actually have kind of full symmetricity of min and max of X and Y. So we can just switch min and max, consider the max and min problem, and there will be a common value of the problem. So what they call strong duality. So there will be a point X star, Y star called the saddle point, satisfying this property. So as soon as you change a bit Y from Y star, you will have a smaller value. So Y star is a maximum for X star, and X star is the minimum for Y star. And the corresponding value F star will be the common value of the two problems. So you can switch them whatsoever, and the convergence of the algorithms is in terms of somehow symmetric quantities with respect to X and Y. So how do you usually prove, how do you usually control the accuracy of any given algorithm? And what would be the accuracy? Using convexity concavity and strong duality. So if I introduce the max function or the primal function phi of X, which is the pointwise max over Y, and I introduce the corresponding mean function psi of Y, which I will not require you to remember after this slide. We will never need it afterwards. Okay, then I actually can say that phi star, the minimum of phi, is equal to the maximum of psi, right? And then I can just write the sum of the primal and dual gap for solving the problem. So let's say that xt yt is my current iterate. Then I can say that I can define xt yt, right? I can define the this quantity, which is called the duality gap. And because of Y star being equal to psi star in this case, the duality gap will not be an upper bound, but will actually be the sum of the primal and the dual gaps. Okay. Now, this I can upper bound using convexity and concavity in terms of this quantity, in terms of the gradient anti-gradient times the X and Y. Okay, and then essentially the point is that now I see that I have to solve the variational inequality, and there is the whole framework of solving variational inequalities. There are methods for solving them, and roughly to reach epsilon duality gap, I will need complexity. I will need to perform one of epsilon iterations with the first order oracle by some version of the extra gradient algorithm from a very high level perspective. Okay, I'm picking into this kind of line a few, many recent papers that refine this theory, that considered what happens with respect to when the objective is strongly convex, strongly concave, lower bounds. But my claim is that my message here is that we basically know how to do this, and this is done by the usually in the primal dual framework. Okay, now what happens if we move beyond this framework? Okay, if we move beyond the setup of convex concave objective function, so how can we move it? Okay, so my general goal is to consider non-convex non-concave problems, but I will start with non-convex concave problems, which by now we pretty much also know how to solve. And actually, we have with Meisam and Moreau, we had a paper that was that has one of a few papers with matching state-of-the-art guarantees, and they conjectured to be sharp, but this is still an open question to the best of my knowledge. But everybody believes them to be sharp. What happens when f is non-convex in X but still concave in Y? Okay, so first of all, I can still, because of concavity in Y, I can still evaluate the primal function efficiently. So I can solve a concave maximization problem to find phi of x at the point x. Unfortunately, I will not have duality. I will not have strong duality, right? And weak duality will not typically be useful here because there are no guarantees you can think of, no reasonable guarantees on the gap between the two. On how much do we lose by passing to the dual problem? So what happens? This, by the way, this explains why I consider non-convex in this slide non-convex-concave problems and not convex-non-concave problems, right? Because in convex-non-concave problems, my first task for any x, I have to proceed in the order of the problem. I really have for any x to solve the problem in y in some sense, to be sure that I'm doing what I must do. That I'm minimizing in x, maximizing in y. Well, in this case, I will not be able even to evaluate my function to minimize phi of x at the point. However, in this case, we can evaluate it, and moreover, we have this function is weakly convex phi of x as a sum of as a pointwise as a pointwise maximum of smooth in x functions, in particular weakly convex. And essentially, we know that for weakly convex functions, you can still work with subgradients. You still have the rules. You still have the familiar subdifferentiable calculus, essentially. And so, in particular, I know that my subgradient will be attained at some y, and I can think about the problem of, well, first of all, I will typically not be able already here to solve my problem or to find the actual phi star, right? Because if you think about it, even in the set where y is a singleton, the set y is a singleton, then this problem here reduces to a minimization problem, which is non-convex. It is smooth now, right? But it is non-convex. And even in this case, a reasonable goal instead would be to find for a near stationary point, a first order stationary point. And so in particular, there has been, we know at least in the case of the singleton y, what would be the complexity of finding first order stationary point. We know that the right algorithm in this case will be simply projected gradient descent, right? We know that the corresponding rate will be optimal, the lower bounds proved by Carmon and others. And moreover, we actually even know that if you have an algorithm, whereas local search can find you first order stationary points, actually, if you add some random perturbations in the right regime, then finding second order stationary points will be as easy, or like as hard, not harder that much. This is work. This was shown by Chijin in 2017 and co-authors, and actually it was extended by Dmitrii Dusvyatsky and Demic Davis for weakly convex functions. So, in other words, okay, we can stop on the problem of finding in this setup. We can think about a reasonable problem of finding a stationary point, first order stationary point of a non-convex, weakly convex, and non-smooth function phi of x. Phi of x is non-smooth because y is generally not a singleton, of course. Okay, so now I would like to define the criterion with which I will be working, and this criterion will, by extension, be used in the non-convex-non-concave case, which is actually addressed in the paper. So to do it, let me first remark that when your function is probably well known, I hope that most of you know it, but let me just briefly mention it, that if you have a function phi of x, which is even if it's convex, okay, but the point is that as soon as it's non-smooth, the question, you cannot just talk about right away about its near stationary points. So think about a sharp function, a function with a kink, like absolute value of x. So we know what is a stationary point. It has a sole stationary point, which is 0. But as soon as you allow for some error epsilon in the non-stationarity, so you can think, okay, I will try to find a point with subgradient at most epsilon, the norm of the subgradient at most epsilon. Unfortunately, it doesn't work this way because of the sharpness. So for any x non-zero, the subgradient, the subdifferential will be a singleton and 1 or minus 1. So you need to get rid of the kinks. You need to smooth out your function, and there is a standard way of doing this. So we will go over it in the next slide. So it's called Moreau smoothing. So now So I will just first of all, I will just directly tell you that we will deal with the Moreau criterion here. So the norm of the Moreau, of the gradient of the Moreau envelope, for those who know. But for those who don't know, let me just mention that there are essentially two ways a priori that you can think about first near stationarity in this problem. Okay, in non-convex concave problems, or non-convex-nonconcave problems by extension. And it turns out that in the non-convex concave setup, the two ways are essentially equivalent. But unfortunately, only one of them carries out to the non-convex-nonconcave case, and namely the Moreau criterion way. So let me now explain what I mean. So we can think about saying that the point xy is near stationary, near first order stationary. Let's say if the norm of the gradient anti-gradient vector, the corresponding gradient anti-gradient vector, right? So here, this guy is smaller than some epsilon. You can reweight them, they actually have different units. You can reweight them, but here's the point, right? So there is a way to extend it by taking into account that the sets are constrained. You can consider the proximal, the norm of the gradient mapping, for example, or there are some other criteria that take into account the constraints. But the point is that it's immediately seen that this is kind of, this is a very kind of symmetric way of treating x and y. It doesn't look good in the setup where x and y are really different variables. Like they have the problem. You don't have strong duality here. Another way is essentially to say, okay, my problem was, so I really want to think about minimization of the primal function phi of x. And so I want to have a stationarity criterion that is defined with respect to the primal function. Okay, but I have the problem with the kinks, so I will smooth them out. There is essentially a way to smooth them out in the right way, using that phi is weakly convex. So if your function had, I did not carry it out as assumption, but the point is that if you assume that your initial function was lambda smooth in x, so for any y, the gradient, the partial gradient in x had norm at most lambda, then your phi is lambda weakly convex. So in other words, this function is convex. And then if you take any bigger regularization value, lambda regularization level, then you have so then this minimization problem has a unique minimizer, has a unique solution. So I can define this function phi lambda of x first of all, right? In this way, where what I minimize is, well, definitely convex function, actually strongly convex function, lambda strongly convex function. And this minimum at any given x is called the standard, I call it standard Moreau envelope for a lambda weakly convex function phi, this phi is like any candidate lambda weakly convex function, and the calligraphic phi, the squiggly phi, is the primal function in the non-convex, in the Minimax problem. So the point is that, first of all, so at least if I take it with lambda large enough, so essentially it's enough to take any lambda larger than 1/2, but if you take it by 1/2 of lambda larger, then like things that kind of like, it's just like a way to standardize this definition. But the point is that I have that this function will be actually differentiable and moreover lambda smooth. So lambda smooth for taking this lambda here. So for this function will not have any sharpness in it, essentially. And moreover, lambda smooth and the same as each component of the initial function with this constant 2 here. So now, moreover, so first of all, like let me just announce you that in the next slide I will, motivate this Moreau envelope criterion, saying that the smoothing makes sense from the point of view of the initial problem, of course. But before doing that, let me just comment that actually in the non-convex concave setup, it can be shown that these two ways are equivalent in some sense. So if you found a point which is essentially a point such that the x gradient has norm at most epsilon, and the y gradient has norm at most, well, roughly epsilon square up to some constants that depend on the problem parameters, then this point is actually a Moreau envelope point as well. So you can think about solving this problem. And vice versa, in fact, that you found a primal point and you find the corresponding maximizer, that essentially there is a way going by doing, I think, by running an extra gradient algorithm, there is a way of recovering such a point in the first definition. Unfortunately, it doesn't carry out to the non-convex-nonconcave setup. So the Moreau criterion makes perfect sense still, because in the Moreau criterion, note that we never use the concavity actually. Why? We only use weak convexity in X, which we still have, of function phi of X. But the first definition fails spectacularly. So there is a very simple example. The function is, it's in the first pages of our paper, but it's a function in 2 variables, which is like cubic, I think it's cubic in Y, something like xy minus phi cube, such that the point, even exact stationary point, is not the min-max point that we want to find. So there is a unique first order stationary point, and this point does not correspond with a unique min-max point. So it's just not the right criterion whatsoever, even without taking aside the question of approximate stationarity. It's just not the right target to look at. This is the reason why we decided in this project to focus on the Moreau criterion. So another reason, so as I promised, let me explain that. Let me motivate. So I will just recall, this is a result taken initially from Lin, but there is a mistake in their paper, which as far to the best of my knowledge, they did not correct. They tried to correct it, but what they proposed is incorrect still. But essentially, here is the result. Okay. As soon as so essentially, if your point X has a small gradient of the Moreau envelope with a norm at most epsilon, so you define the corresponding minimizer, which is unique by strong convexity of this function, which I will say is X plus the proximal mapping of X. Okay, then what you have is first of all, you will have a X plus, so essentially what you will have is what you want to have, okay? So you will have that, first of all, this point X plus will be close to your X. And second, in this point X plus, you will have a small value of the projected gradient, small norm of the projected gradient. So in other words, X plus is the point that you would like to output, really. Okay, and so it is guaranteed that, well, I mean, okay, so this is not what I said, but here's the guarantee. First of all, if in X, if the Moreau envelope gradient norm is smaller than epsilon, then the corresponding proximal mapping, so there is another point X plus, which can be actually computed, the proximal mapping of the point X. So which will be, first of all, close to this point X. And second, for some subgradient in the subdifferential of the primal function at this new point X plus, the corresponding proximal gradient norm will be small. Okay. And in some sense, this is the right amount of closeness. Okay, so if you take at least the units correspond, the units are correct here. In some sense, this tells you that it's right, it's okay to look at the Moreau envelope gradient. And this is the criterion we will be using. So, and let me just give you the definition. I call a point epsilon professor stationary in a min-max problem with primal function phi of x without assuming convexity or concavity, but only assuming smoothness, lambda smoothness of the functions f of x for any y. If the gradient of the corresponding Moreau envelope, standard Moreau envelope, is at most epsilon in the norm. Okay, so now what are the challenges? So from now on, our goal is to find, oh, I'm sorry, I have to change the file. It's not the right. I believe this is not the right file that I opened. Oh no, actually it is the right file. That's fine. So, okay, so what are the challenges? So let's say for simplicity that first of all, I assume I will talk about the Lipschitzness of x, of the gradient in x, of the x gradient of f. And moreover, I will even consider inhomogeneous, like heterogeneous smoothness in the two variables. So I assume that for any y, the gradient in x is lambda Lipschitz with respect to x and mu Lipschitz with respect to y. So mu is the interaction, is the coupling parameter, and lambda is the homogeneous XX smoothness parameter. So in particular, phi is lambda weakly convex. And my problem of interest is this, right? So given a target epsilon and a problem instance in this form, I must define an x star. It should be x star here, I'm sorry, such that the norm of the Moreau gradient of the Moreau envelope gradient at x star is at most epsilon. By the way, here it might not, if x itself, set capital X, is not compact, exact stationary point might not exist, but that's fine. For any finite epsilon, the corresponding point will exist. Epsilon strictly positive. So now the problem in this problem right now, as of now, is as soon as I give up concavity in y, so here I do not assume concavity in y anymore. Okay, so it turns out that tractable ways of solving such problems usually either they assume that in y the criterion is concave, or they elsewhere they somehow assume that the maximization problem, the nested maximization problem, can be solved globally somehow. Sometimes they just postulate it, for example. Lin and others, they consider an abstract maximization oracle and ask the question, what is the complexity with this oracle? Why is that? Well, essentially it's because of the Lyapunov type analysis. If you try to analyze convergence of such algorithms, because essentially, roughly, because you cannot switch min and max, they really have different importance, and you really have to analyze the problems with like phi function inside. And phi function maximizes over the whole y, or on the whole set. Like phi function, the primal function, is defined in terms of the global maximization, the full maximization, not local maximization, or something like that. And so essentially, this is kind of the restriction of the methods, and we would like to get rid of this restriction. Okay, so we started to think about how to get rid of this restriction. And the key insight is that, okay, at least we know one trivial example where this is possible. If y is a singleton, there is no question with maximization whatsoever. Okay. The question now is, does this carry out to non-trivially to non-singletons, but sets of the small size? And it turns out the answer is yes. And so before we move this, let me just briefly mention where it can be useful. If you think about such problems from the applied perspective, of course, it's adversarial training. It's adversarial training, and more generally, it's training of or like optimization of any system with small perturbations. So, so in particular, in adversarial training, you minimize. Let's say if you think about ERM objective, ERM type objective, then you minimize the adversarially perturbed objective, where the loss functions are non-convex in your parameter theta. Theta is in the role of x, and typically non-concave in your perturbation. So if you think about robust training of deep neural nets, for example, this will be the case. And the perturbations will be small usually by design, right? Because if the perturbations are large, essentially we will be able to eliminate them as outliers. They will be visible. The whole point about robustness, about adversarial robustness, is that the perturbations should be, they cannot be too big, otherwise you will just detect it. They should be small, but at the same time big enough to shift, essentially, to shift your baseline. This kind of small max domain, small maximization domain assumption is rooted in practice, in fact. So, okay, now let me just go over the strategy. So the idea is to say, okay, so why we assume the small domain in Y? Well, the idea is that if we replace pointwise for any x the criterion f of xy by this kth order Taylor approximation, then for small order of approximation, the problem will become tractable in Y. So in particular, in the case of zero order approximation, so just constant approximation, there is no problem of maximization whatsoever. For first order model, you will have an affine function, which you will be able to maximize in Y, even with a linear maximization oracle over a simple set, over an LMO set. And in the quadratic case, in the case of second order approximation, you can your problem will not be, your objective is non-concave in Y, but you can actually maximize with the first order oracle non-concave quadratics efficiently. So in particular, this is the paper of Carmen and Dmitrii that state-of-the-art guarantee. In other words, now what is our strategy? Our strategy is to say, okay, we assume that Y is a small set, small enough for the global approximation, global Taylor approximation to work. What this means, I will explain in a second. And we just replace, just instead of the problem f of xy, we consider this problem where f hat k of x, y is simply the function in which you take the k order Taylor expansion in y of your f for any point x. So you are at the point x, you look at the corresponding Taylor expansion of the function with frozen x and changing y. The center of this approximation is fixed in advance throughout. So there is a y hat, which is the center of the Taylor approximation. And then you just solve the corresponding min-max problem. Okay. So the strategy is, first of all, to prove a general approximation guarantee that for the diameter, so let me call d the diameter of y, the Euclidean diameter of y. So let's prove, we are aiming to prove that for d small enough, where small enough is, we expect some power of the target accuracy epsilon to be specified. And depending on epsilon and the order of the Taylor approximation, with constant factors packed inside this all depending on the smoothness parameter, the regularity parameter of your function f. So we expect for d smaller than some threshold, we will have a guarantee that any epsilon first order stationary point of this problem will remain over epsilon for stationary for the initial problem. And in this sense, Taylor approximation is good enough. And this is the approximation theory part of the paper and of this whole business. So you prove this kind of guarantee, and hopefully you're even able to prove that these guarantees are sharp. So this is the d bar. This is the critical diameter. It cannot be smaller, or it cannot be bigger. As soon as you go beyond d bar, this guarantee breaks. You will have a point which is stationary for the surrogate, but not for the initial problem. And then if this is the case, if you manage to do it, then what you can do is simply, okay, if you're able to solve now, you have some ad hoc algorithms for solving this problem, which is way more structured. Something roughly, you can think about gradient descent ascent scheme. Okay, because for these problems with small enough k, you can perform maximization in Y. So essentially, these problems are very well structured. Then you can essentially use the first part of the strategy and just say, okay, I find an epsilon stationary. Now it's like 2 epsilon stationary for the initial problem. I'm done. Okay, so this is the strategy. So I will not talk about the second part, see the paper, but I will talk about the first one. So about this accuracy. So essentially, here is my exact assumption. Okay, so I assume because I'm going to now for the first part of the strategy, for this approximation theory part, actually this part of the strategy we figured out for any k, with sharp bounds for any order k, even though in the algorithmic from the algorithmic perspective we only need small k. And so here are our assumptions. So correspondingly, because we consider approximation with arbitrary order k, we should have the matching regularity assumption in Y. So now I specify the Y regularity. Finally, I say that there is a parameter rho k such that the corresponding tensor of Y partial derivatives at every x is uniformly rho k Lipschitz. So it's just an extension of the Lipschitzness of the gradient, but for potentially for higher order tensor. Okay, and I can actually immediately remark that by integration and Taylor expansion, I can show this guarantee that actually I recall you that f hat k is the Taylor approximation of f and y, of the matching order k. So this is the matching guarantee of the corresponding guarantee of the function values. So for any xy, your function, your Taylor approximation will be at most this much, so rho d power k plus 1 over the factorial apart from the function value. So this is the function value error of Taylor approximation. So if you also assume higher order, so if you assume also Lipschitzness of this tensor in X, so in addition to the X assumption with some sigma k, then essentially you will have the error of approximating the X gradient of the function here. Okay, and this will be helpful, but let me just briefly mention that this sigma k is almost non-participating in the theory, as you would expect. Like we already, for xx regularity, we already have a lower order parameter, lambda. And so we expect that sigma k will not control much of stuff going on here, and indeed it doesn't. So in particular, sigma k is just 0 in the problems with bilinear coupling, with bilinear interaction, first of all. And second, even with the problems with general interaction, the corresponding terms in the upper bound for the critical diameter, the terms including sigma, they are higher order terms with higher dependency on the diameter. And so they essentially vanish in the interesting regime of small diameters. So now let me briefly just mention that. So without going into much details, it can be shown that first of all that the primal function in the approximated problem, which I call phi hat, I emit the k index. So it's actually lambda, it's essentially it's lambda plus something small weakly convex. Okay, so you would expect it to be almost as good weakly convex as the initial function. A priori, it's something to be proved because strictly speaking, nobody guaranteed you that your Taylor approximations will be smooth in X, but actually they will under these assumptions. And moreover, the additional smoothness will be, the additional margin of how smooth they are, it will be very small compared to the initial one. And this is something that, so for the sake of this discussion, I just treat the smoothness of this function as the smoothness of the initial function. And the paper, everything is properly done. Now, my question is, okay, so here is my question, and here is the answer to this question. What is the d bar? So I recall, so what is, so for how small the diameter d of y is allowed to be such that if x star is an arbitrary epsilon fsp in the surrogate problem, then this point will be O of epsilon in the fsp in the initial problem as well. So here is the guarantee. Actually, such a point for any k with a matching regularity assumption. Here is essentially the equation that defines the d bar, and here is the result of this equation. So if you solve for d bar for this equation, this is what you get. So first of all, so let me comment on this result, and then we will be able to prove one part of this result. So this there are essentially two bounds to prove. So first of all, let me just comment on this result, and then the remaining 5 minutes of my time, I will go over the proof of the first bound here. So first of all, if you believe me, if you solve this kind of stuff, well, first of all, you see that the part including sigma k is really not important because it has higher order in d, and d is something small, and it's additive. The term is additive. The corresponding term is additive to the term mu d, which has lower order in d. So this is kind of a small thing, and roughly sigma k does not change anything. What you have here is that at least one of two things in terms of d should be smaller than epsilon up to a constant. One thing is mu d. So mu is the coupling parameter. It's the cross-Lipschitz constant, the Lipschitzness of x gradient with respect to y, or vice versa. So mu d should be smaller than epsilon. In other words, according to this, d should be linear in epsilon at most, which is kind of not very cool. So d, the diameter smaller than the accuracy is not great. But fortunately, you actually can choose the best of the two worlds. So the other bound does not depend on coupling whatsoever. It only depends on the homogeneous smoothness parameters. And it has higher order in d. So as soon as k is equal to 1, the order is the same. And you simply choose between mu and the square root of lambda rho, which have the same units. And it's kind of like coupling. Essentially, the relation between the two is the relative level of coupling, of interaction in your problem. Now, in the higher order of smoothness in y, only in y, you can benefit. You can benefit from this bound because here the dependency of d will have higher order. And so if you solve with respect to d, in other words, d bar is allowed to be the biggest, the larger of the two expressions, epsilon over mu, and this thing, k times this. Where actually this, there is a constant here, hidden constant here. Moreover, I actually claim we have a bound which is, to my own surprise, it turned out that this whole business here is optimal. So both bounds are optimal. So the lower bound on d bar has the same structure. We did not recover the additive term, but at least we recovered the same structure with k factorial instead of k plus 1 factorial, which cost a lot of technical effort. So essentially, this is the right picture from the point of view. This theorem is sharp for any order k. This is the message. And in particular, for the interesting case from the algorithmic perspective really is the case of the second order approximation, because in this case, we can solve the corresponding surrogate problem also algorithmically. And in this case, d is allowed to be as large as epsilon 2/3, essentially. So now let me prove one of these two bounds. So essentially, the story is that surprisingly, this bound is way harder to prove. It's way more technical to prove. I will need essentially about 10 minutes, and I don't have this time. So this bound is essentially simple to write because it's roughly here, the most interesting points. But technically, it's more challenging. But the challenging, technically, analysis, although technically challenging, is something like more conventional, somewhat more conventional to what you would expect. And this one is easy, but somewhat surprising. So this part simply relies on the uniform closeness of the gradient. So this bound is actually stronger than what is stated here. So the second bound is precisely what's stated. It's you have x star to be epsilon FSP, then it will be a 6 epsilon FSP in the initial problem. The first bound, however, is uniform, it's stronger. It says that for any x, the gradient of the Moreau envelopes of the corresponding of the surrogate and the target function are close, uniformly close, this much close. Okay, and so let me just present the proof, and we will be done. So the proof is very simple. So essentially, first you use the Moreau envelope gradient characterization. So essentially, just from the first order optimality condition for the Moreau envelope, you can express these gradients in terms of x and its corresponding proximal mapping, x plus or x hat plus. So x plus is the proximal mapping of x with respect to phi, and x hat plus the same, but with respect to the approximated primal function. Okay, so in other words, this allows you to just think about how close x plus is to x hat plus. So how much this Taylor expansion perturbs your proximal mapping, right? Because the two they correspond. Okay, so now how to bound it? This is easy to bound. You use the strong convexity of the two functions. So the function phi is lambda strongly convex, and the function, the regularized function phi. And the regularized function phi hat is kind of almost lambda strongly convex. So up to this negligence of the higher order terms, as I mentioned in the beginning. And x plus and x hat plus are their corresponding minimizers, unique minimizers. Okay, so then you write these conditions, you add up the two inequalities, and you can, this allows you to upper bound the norm, the squared norm of the difference between x plus and x hat plus. In terms of simply the function values. But the function values, you know that they are uniformly close. Simply, well, this is an easy step, but you know, by doing some, you know, maximum calculus, it's easy to see that this whole, the right-hand side is upper bounded by uniform function value error of your Taylor approximation, which is this. Okay, which itself is done by integration. This bound, I stated it without the proof, so it's done by integration, Taylor expansion. So this is a standard. So let me just, before I proceed to questions, let me just briefly you know, just discuss the coupling dependent bounds. So the main ideas is that essentially the first step was, of course, the optimality conditions, and you again analyze this norm, the norm of the difference, but this analysis is way more involved, it's way more technical. There are several steps of using strong convexity here and there, some Cauchy-Schwarz magic, and finally, you know, the explicit characterization of the subgradient of the max, of the subdifferential of the max type function. So it's used explicitly that for maximum over weakly convex function, the Fréchet subdifferential has explicit structure as a convex combination of the non-vanishing subgradients, Fréchet subgradients. Yeah, so this is just, I will not comment on this. This is essentially how much we neglected this weak convexity of this function, of the approximated primal function. Thank you. Any questions?
One quick question. So here you really are specializing to, if you want to view it as a game, a two-player game, a max-min problem, not multiplayer game, for instance.
Oh, yeah, it's a good question. I did not think about the multiplayer scenario, but I think it's not. It's kind of like it can be naturally extended. Like, right? I did not think about it technically, I should say. But right now, I don't see anything which would prevent such an extension really structurally. So it really relies on the maximization in Y of low order models of your function.
Yeah, potentially.
So I think that can be extended, but I'm not sure.
Right. The idea can probably be used for multiplayer case where each is updating a partial gradient, at least the part of your.
Yes, yes. I mean, yeah, I don't see how this is really that much specialized to the two-player setup. It is specialized to treating X and Y in a different way completely. So this is kind of the core idea. There is no duality here whatsoever, to the best of my understanding.
Yeah, thank you.
Sure. Any questions more? I will be happy to discuss. Anticipating a question about the stochastic setup, I did not think about it.